Hello everyone, this is Cyrus from AIML. My topic is recurrence relation. Yes. Sequences are ordered list of elements 1, 2, 3, 5, 8, 1, 3, 9, 27, 81. Sequences arise throughout mathematics, computer science, and in many other discipline- disciplines ranging from botany to music. We will introduce the terminology to present sequences, that is, recurrence relations. Definition. A sequence is a function from subset of the integers, usually either the set 0, 1, 2, 3, so on, or 1, 2, 3, 4 to a set S. The notation AN is used to denote the image of the integer n. You can think of an as the equivalent of fn, where f is a function from 0, 1, 2 to set s. We call an a term of the sequence. For example, if you consider the sequence an where an equal to 1 by n, where an equal to 1 by n, where 1 starts n is from 1. N is greater than or equal to 1. 1 by 1 is 1, 1 by 2, 1 by 3, 1 by 4. This is the sequence for the given condition, that is an equal to 1 by n. If we substitute in the place of n, if we substitute 1, 2, 3, and so on, in the place of n, we'll get the sequence. So this is the sequence we will get. This we will call it as recurrence relations. A recurrence relation for the sequence an is an equation that expresses an an in terms of one or more the previous terms of the sequence, namely a0, a1, a so on, an minus 1 for all integers n with n greater than or equal to n0, where n0 is a non-negative integer. Means here the sequence should be in the same sequence for the previous and for the next integer, next value. The sequence should be the same. There should be the same relation between the previous and the next one. That is called the recurrence relation, where n is greater than or equal to n0, and also the n0 should not be negative integer. That should be non-negative integer. A sequence is called a solution of a recurrence relation if its term satisfies the recurrence relation. This sequence, whatever the sequence we have discussed, that is called the solution of a recurrence relation if and only it satisfies where n is greater than or equal to n0, where n0 should not be in the negative form. So that we will call it as a solution. If the term satisfies the recurrence relation, the initial condition for a sequence satisfies the terms that precede the first term where the recurrence relation takes effect. Definition. For example, if you take the Fibonacci numbers means the Fibonacci sequence of f0, f1, f2, and so on is defined as initial condition f0 equal to 0, f1 equal to 1. Initially, the two integer values are 0 and 1. Then, if we apply the recurrence relation for the Fibonacci sequence, so we'll get recurrence relation in fn equal to fn minus 1 plus fn minus 2. If we want to get the f2 value, we have to add the 0 plus 1. So we'll get the sequence. If we want to the sequence f3 value, we'll add f1 and f2. Adding previous two values, so we'll get the present value. Finding a formula for the nth term of the sequence generated by a recurrence relation is called the solving the recurrence relation. For example, if we discuss, if I want to find the value of fn value of Fibonacci series, so what is the formula? Fn minus 1 plus Fn minus 2. If we find this nth value of the Fibonacci that sequence, so we will call it as a solving the recurrence relation. Such a formula is called a explicit or closed formula. One technique for finding an explicit formula for the sequence defined by a recurrence relation is backtracking. By using the backtracking, we will find the recurrence relation. One technique for finding an explicit formula. To find out this formula of this sequence by using backtracking is very easy. For example, let A and be a sequence that satisfies the recurrence relation an equal to an minus 1 plus 3 for n equal to 2, 3, 4, and suppose that a1 equal to 2. Find an explicit formula for the sequence. We have to find here explicit formula for the given sequence, given recurrence sequence, where n is greater, where n equal to 2, 3, 4, n is greater than or equal to 2, where and a1 is given as 2. First, we have to write given formula an equal to an minus 1 plus 3. In place of an minus 1, we have to write an minus 2 plus 3. That means here n is there, here n minus 1 is there, here n minus 1 is there, here n minus 2 is there. Because here the preceding value of an we have to write here. Preceding value of the n value is an minus 1. Here the preceding value of an minus 1 is an minus 2. An minus 2 plus 3 and 3 is as it is. Finally, get the an minus 3 plus 2 into 3. 2 into 3. So, for an minus 2, you will write preceding term of an minus 2 is an minus 3 plus 3 of 2 into 3. 2 into 3 is as it is. Then again, it is 3 into 3. Like that, we will substitute likewise a2 plus n minus 2 to 3 equal to a1 plus 3 plus n minus 2 into 3. Finally, we will get the formula as 3 into n minus 1. Linear homogeneous recurrence relation. What is? Till now we had discussed what is recurrence relation. In that, what is linear homogeneous recurrence relation? A linear homogeneous recurrence relation of degree k with constant coefficient is the recurrence of the form. It should be in the form of an equal r1 an minus 1 plus r2 an minus 2 plus so on rk an minus k, where r1 comma r2 comma so on rk are real numbers and rk should not be equal to 0. It is a linear because the right hand side is the sum of the previous terms of the sequence, each multiplied by a function of n. It is homogeneous because no terms occurs that are not multiplied of that into a. Each coefficient is a constant. Here r1, r2, rk are the constant, and we have the different terms an minus 1, an minus 2, so that will call it as homogeneous and linear. The degree is k because an is expressed in terms of the previous k term of the sequence. The degree is k because n is expressed in terms of the previous k term of the sequence. Here pn equal to, for example, 1.11 p of n minus 1, whether it is linear homogeneous or not. Linear homogeneous recurrence relation of degree 1. Here the degree is 1. Fn equal to Fn minus 1 plus Fn minus 2. Here also the degree is 2 and also it is a linear homogeneous recurrence relation. Here n equal to n minus 1 plus an square minus 2. It is not linear because it is not in the same sequence. Here an minus 1 is there, here an minus 2 whole square there. So it is not a linear homogeneous recurrence relation. Hn equal to 2hn minus 1 plus 1. It is not a homogeneous. Bn equal to n into bn minus 1. Its quotients are not constant. Here the quotient is not constant. It is varying according to the n value. Algebraic manipulation yield that characteristic equation is x power k minus r1 x power k minus 1 minus r2 x power k minus 2 so on rk equal to 0. The sequence n with n equal to a x power n is a solution if and only if x is a solution to the characteristic equation. It is a solution. This is a solution if and only x is a solution of the characteristic equation. This if the x is solution for this characteristic equation, then only will say this is the solution. N equal to x power n is the solution. This is all about the linear homogeneous relation, recurrence relation, and what is recurrence relation, and we have seen the some of the example here. One of the example of the recurrence relation, that is sequence which follows the preceding and the succeeding in the same manner. So we'll call it as a recurrence relation. So this is the all about the recurrence and linear recurrence homogeneous. Thank you.